Welcome everyone. In this video we're going to learn how to plot cubic functions in translated horizontal inflection form. The translated horizontal inflection form of the cubic function is y equals a x minus h the whole cube plus k. Not all the cubic functions can be written in this form. We know that the general form of the cubic function is y equals a x cube plus b x square plus c x plus d, and only functions which has b square equals 3ac can be written in this in this translated horizontal inflection form, and such functions have the graph which looks similar to that one. Okay, and these type of functions can be drawn by applying the simple transformations to y equals ax cube, the simple cubic functions. And in this video we are particularly learning how to make the transformations from this simple cubic function to this form. Also we'll be learning how to plot cubic function if this form is given. Okay, the first thing that we get from this form, the translated horizontal inflection form, is the center point of the cubic function without using any equations. The center point is hk. Now also this is an inflection point and a stationary point as well. If you draw a tangent at the center point, it will be a straight line, a horizontal line parallel to the x-axis. Also at this point, the concavity changes from being hill shape to a valley shape. Okay. And now what are the different kinds of transformations that's applied to this function to get to this function? We already learned this kind of transformations in quadratic functions. It's quite similar when we apply in here as well. The type of transformation that we can apply are reflection, dilation, horizontal translation and vertical translation. Okay, let's first learn about reflection. If you look at two simple functions, y equals x cube and y equals minus x cube, these two functions have a equals plus 1 in here and a equals minus 1. So a is greater than 0 here and a is less than 0 here. So let's have a look at the two different graphs in here. So the red one shows this y equals x cube and the black one shows y equals minus x cube. So one is exactly the reflection of the other one. So the sign of I determines whether the graph is reflected or not about the x-axis. And now the size of I, how does that matter? Let's look at two graph with I equals x cube and y equals 2x cube. In this one a is 1 and this is twice that amount. How does that two graphs looks like? So let's have a look. So first one is the y equals x cube is a little bit more wider compared to the other one. So the y equals 2x cube is dilated from the x-axis. So if you look at two numbers, if you plug in two values for x, for example x equals 1, y is 1 in here, and for x equals 1, y equals 2 here. So the y, the function increases twice as quickly for this function. So that's why it's more close to the y-axis. And a is known as the dilation factor. Let's now look at the horizontal translation. The horizontal translation is determined by h. If h is positive, the graph is translated to the right by an amount h, and if h is negative, it's translated to the left. Let's have a look at an example. Y equals x cube is the red one in there, and y equals x minus 2 the whole cube is the black one. How does that differ? So if you compare these two equations, you can see that h equals plus 2. You might be tempted to say h is minus 2, but it's not, because x minus h in here. So when you compare these two equations, it's h equals 2. So when h is positive, the graph is translated to the right, or when the equation is of the form x minus something, the graph is translated to the right by that much amount. And if the equation was of the form y equals x plus 2 the whole cube, the graph could have been shifted to the left because h is then minus 2 by 2 unit. Now let's look at vertical translation. Vertical translation is determined by k. If k is positive, it's translated upwards by k units, and if it's negative, it's translated to the down by k unit. Let's have a look at two functions, y equals x cube and y equals x cube plus 3. So you can see in here, this graph is simply a vertical translation of this one by an amount 3. So the graph is shifted upwards by units 3. So if the equation was y equals x cube minus 3, then it should have been shifted down by unit 3. That's all about the transformations. Now let's have a look how we can plot a cubic function if this form is given. Okay, let's now plot this function y equals 2x plus 1 the whole cube minus 2. So this is simply a set of transformations applied to this one, dilated by a factor 2, and then horizontal translation by minus 1 and vertical translation by minus 2. But instead of doing this, applying these transformations, which could be a little bit tricky to plot, what we're going to follow is find the center point, which is quite easy if we are given with this form, which is hk, and that's minus 1, minus 2 by comparing these two equations. So we got the center point, and this is also, as I said before, it's an inflection point and also a stationary point or stationary inflection point. And okay, so to plot this function, we need at least 4 points to plot it in a proper way, because any function of degree n requires n plus 1 points to plot it in a quite decent way. Okay, so this is 1 point, and the next thing, easy one, is y-intercept, and another one is x-intercept, and maybe 1 or 2 points to make n plus 1 points. In this case, it's a 4 points. Okay, so y-intercept is when x equals 0 in this equation. So that's y equals 2 times 0 plus 1 cube minus 2 is 2 minus 2 is 0. So that's y equals 0, or the y-x-intercept, the point is 0, 0. So this is fortunately the x-intercept as well, because x-intercept is when y equals 0. That's already x equals 0. Okay, so we got only 1 point by doing these two. So 1, 2, and we need to get 2 more points to plot this function. So randomly choose 2 points, one on either side of the inflection point. So let me put x as 1, and then y becomes 1 plus 1 cube is 8. 8 times 2 is 16. 16 minus 2 is 14. So 1, 14 is 1 point. And let's find one more point. Minus 1 is already this center point, so we don't have to substitute that one again. And put minus 2. Minus 2 makes minus 2 plus 1 is minus 1 inside the bracket, which when cubes as minus 1. So it's a minus 2. Minus 2 is minus 4. Okay, so that's minus 2 minus 4 is another point. So we got 4 points. Now let's plot the graph. So this graph is not to be scaled properly because this is 2 unit and this is 1 unit, which is not exactly proper. So I wanted to fit that one in here. So the first point which I'm going to mark is the center point, which is minus 1, minus 2. That's this one. That's a minus 1, minus 2. And another point is the center point, the x and y intercept, which is 0, 0. Another point which we got is 1, 14, which is here. And the last point we found is minus 2, minus 4, which is here, minus 2, minus 4. Now let's complete the drawing. So this is an inflection point and stationary point. So we need to make a little bit straight, because if you draw a tangent here, should be a straight line up here. So it's something like that, and then goes something like that. I'm not very good in drawing, but I have made as much as I can, and also a graph is shown in here. I've given a graph of y equals x cube as a reference, and you can see the kind of transformation that has applied to this one to get to this one. I hope this makes sense to you. In summary, we've covered the kind of transformations that has applied to this basic, the fundamental cubic function to get to this one, and also learn how to plot a cubic function if this translated horizontal inflection form is given.